Design of concrete structures, chapter 4, flexural analysis and design of beams, example 2, part B. So we continue our previous problem, and which we just doubled the amount of bending moment in previous problem from 45 feet times kilopounds to 90 feet kilopounds, and we just understand that it's not anymore a elastic domain of and with on crack section, so we are still in domain of elastic, but we did the section is goes by some cracks. So then we just review the stage of stresses and strength uh, in a flexural member like beams, and their categories like 1, 2, 3, and we just understand our case. It's not anymore in section 1, and it's in either section 2 or 3. So we just go one by one and just try the second one to see if that's um, fit in the second category or not. If not, just continue with the last, and then calculate moment of crack, and we just understand that our initial moment, which is available moment of 19 feet kilopounds, which is converted to inch pounds, and that's 10 uh, 80 times 10 cubed inch pounds, and that's, you can easily see it. 1080 is almost a double of 593. That's definitely bigger than that. So we are the section is definitely cracked. So then we just understand if m is higher than m crack, it should be either category 2 or 3. And if we just double check this, we just assume that this is the it is second category, and then double check the criteria of that part. So that was what we reviewed, calculated in previous problem in a brief format. And then if we just verify that our stress in compressive part of concrete is a less than, which is 2m over b times k times d squared times j, is a less than half of compressive strength of concrete, which is f prime c, then we are in the second category. If not, we need to move forward in next category or step. So that should be less than half of f prime c. We we did some calculation, and we talk about a criteria and categories and their own criteria, but we never calculated the stresses in second category. So if section cracked, so you can easily see the neutral line comes up, so we have no nothing here in comparison to previous condition, which we have elastic but and uncracked section, which we had, yet we had concrete in a tensile part of the cross section in previous condition, but here you can easily see we have two parts: the compressive concrete at the top and tensile steel, which in a transformed section converted to a equivalent concrete. And in such case, if we just consider a triangular distribution of stresses of equal, which is, if we call this distance kd, the coefficient times the effective depths from the top of the section to the centroid or neutral line, and if this is kd, the length of this part is kd, so definitely the compressive force of concrete applies at 1/3 from the base. The centroid is over there. And definitely the other part is, if you call that J times effective depth, definitely J times another coefficient times effective depth, definitely the total effective depth minus a 1/3 if this distance is JD, the distance of two forces which we are going to develop all coupled. So that's a compressive side of all coupled, and this is the tensile, and the vertical distance between these two are is equal to J times D. So if you compressive force of concrete, tensile of steel, and that's if you just take D out of the equation, that's D times open parenthesis 1 minus a third of K close parenthesis. If you develop the moment, moment is nothing but an arm, so that's a compressive CC times JD. So that's a compressive force of concrete times the distance for moment. That's then the force itself is the area of this distribution, a half of stress, compressive stress in concrete times B times KD. B is the other dimension in which is vertical to normal to the board, and times KD, which is again this distance. That's KD. And then times JD, which is our arm. So our moment is force times arm. And if you do so, it gives us a moment of half of FCC times BKD squared times arm, which is JD. If you replace this equation just based off FCC, it just gives us a compressive stress in concrete, which is 2m over BKD squared times G. That's the stress, compressive stress in concrete in a elastic domain of stresses, but a cracked section. That's a cracked section. A distance from top to the neutral line is KD, coefficient times effective depth. And if we call this part as a transformed area, that's N times area of steel, and A is the modulus of elasticity of steel over concrete, which goes by a number of N. Definitely a modulus of elasticity is much higher than a concrete one, and that's definitely 5, 6, 8, 9, or so on. So AT is N times AS, and if we just develop our equation, so AS, area of steel, tensile force is equal to compressive force in a balanced condition, so AS times, and this is Hooke's law, which says a sigma times epsilon is sigma, and that's equal to A transforms. So when a steel transforms to a concrete, definitely epsilon C for S, which is it was originally a steel, but now transformed to concrete. So we can definitely cancel these two out because they are now identical to each other. And then if we just develop the moment based off a tensile force of steel this time, that says moment is force Ts times Jd times R. That's equal to AS Fs times Jd. So it just simply gives us a tensile stress in steel rebars is equal to a moment over AS times couple arms, so that's J times D. So far we calculated, we know we are in the second category now. Then we just now we do know how to calculate all the stresses for each part, concrete part and steel rebars in cracked section analysis. And then if you just go by a summation of forces goes zero, it just says Cc is equal to Ts. Cc compressive force in concrete is equal to the tensile force in steel rebars. Cc stands for force of concrete. Ts stands for force of steel. That's a half of FCC times B times K times D is equal to ASFS. And then if you expand the equation based of Hooke's law, a half of sigma FCC stand for sigma. Sigma is modulus of elasticity times epsilon. And if we just replace the equation based off of relation of strengths, it just gives us a half of epsilon cc over epsilon. If you just take epsilon s to denominator of the first side, that a half of epsilon cc over epsilon s is equal to a times bkd. The rest is remains the same. That's as times es over, you just take the modulus of elasticity of compressive concrete down to the denominator of the second part. So at the same time, epsilon cc is exactly epsilon u. Epsilon ultimate of concrete is definitely at the topmost of concrete compressive part. That's epsilon for concrete, and at the topmost, which is the highest compressive effect. And if you just go with the relation of epsilon cc over epsilon s based off these triangles, it just says epsilon cc, which is epsilon u over epsilon s is kd over d minus kd. This is d minus kd. So in such case, you can easily rewrite the equation based off a kd and d minus kd. And if you multiply that equation, so that's a half of, if you just take this part to the other side, so that's a half of b times kd squared plus na kd minus a n times as times d, that's equal to 0. If you simplify this equation, we eventually reach to this one, and then this is, if you made it a bit more clear, that's a half of bx squared plus n times as times x. If we just call x of k times d squared, a, let's put it this way, if we call this part kd, it is turns to be all x here, so that's a half of b times x squared plus nas times n times as times x minus n times as times d. So if you proceed the problem, it just gives us a second degree equation based off x, which x is kd. If we solve this second degree equation, it just gives us what kd is, and we can just simply replace that in the equation to get the stresses. So just in case to be in the same page, so if you replace the numeric value of our problem, a half of b, which is a width of section, which is 10 inches, times x squared plus n, which is 8, as was 2 times 3, 7 for 3 in row rebars, times x minus again 8 times as times effective depth, which is 23 inches. If you solve this equation, it just gives you 2x, x1 is a positive and x2 is a negative. Definitely we cannot go with negative answer, so because that should be a positive number, so definitely x1 is 7.63 inches. So, and x, if you remember, that was kd, so x is equal to k times d. So we do know what d is 23, so k is a 0.33. As soon as we calculate a kd, so we can easily calculate k, which is k, we already did it, it's 33, and j is 1 minus a third of k, so that's a 0.89. So then fcc, compressive stress in concrete, is 2 times available moment over bkd squared times j, and fs, stress in tensile stress in steel, is just 1m over as times j times t. So if you replace the numeric value of k and j, which we just calculate them in the equation, you already know what the moment is. That's 2 times 1080, 10 times 10 cubed over b, which is 10, k, which is, we have it here, 0.33, a d squared, which is 23 squared, times j, which is 0.89. And if you replace that in the equation, it just gives you a compressive stress of concrete is 1,319 pound square inches. And if you just replace that for in equation for a steel stress, it just gives us a m over as times j times d, and it just gives us a tensile stress of rebars is equal to 2,220 22,261.67 psi, much higher than stressing each rebars, which is just uh, not each rebar, the total rebars is equal to 22,000 in comparison to a concrete section. So we work around to solve more problem and expand it to the rest of the problem, which is the flexural extent. That's a design load, a for the last category. Thank you.